So once again, my name is Dmitry Samin. I'm with Casper, and besides taking pictures for the slideshow, I also do some crypto. So let's start. I'll try to move really fast, not to delay the next speaker. So Casper is a password company, so that's why we are here. We help digital forensic investigators from police, law enforcement, and government agencies to work with encrypted electronic evidence efficiently. So our software detects encrypted evidence, decrypts it, breaks passwords, and that's why I'm here. So a very short overview of the presentation is that we'll talk about encryption in general, we'll talk about cracking passwords, and we'll see how memory images could help us in this task. So first of all, encryption. So nowadays, usually password is taken, hopefully some random information like salt, and then a special function is applied to get an encryption key out of that. So this function is called key derivation function, or KDF for short. So when we have user data, when we have an encryption key, when we have an encryption algorithm, we could encrypt the data and decrypt it, vice versa. So KDFs actually improved dramatically during the last several years in software that's used nowadays. So let's have a look. Let's start with Office. In Office, before Office 2003, there was like no protection at all. You could get the files encrypted instantly. Office 2003 used MD5, and it used less than 10 iterations of MD5 to hash a password. It also used just 40-bit encryption, but 10 iterations, it's not really secure. Office 2007 introduced SHA-1, 50,000 iterations. This was just a quantum leap in terms of security of Office applications. And I would say that Office 2007 is secure enough for most of the applications. We are not speaking about military, etc. In Office 2010, nothing basically changed except for the iterations. Number was twice as large. And even to attack Office 2007 and Office 2010, I would advise to use GPUs because otherwise it takes too long to find a password. Another example of KDF is password-based KDF2 by RSA. So it's really very used nowadays. Wi-Fi, WinZip, iWorks, OpenOffice, the latest version of Mac OS X, they all rely on this KDF2 for encryption. Another example, Acrobat Adobe PDF, version 9 that was current just approximately 1 year ago, password cracking speed was over 1 million passwords per second. And this is for CPU only, without any hardware acceleration. And this was changed in version 10. Adobe actually added anti-GPU protection there. This is the first time I see this kind of protection in very widely used application. So there are multiple rounds of encryption in KDF, and for each round, different algorithm could be chosen, and this choice depends on the results of the previous round. So go and try to implement this in GPUs. It's really very complex. So what this means for us is password cracking gets slow, and really very slow. So what could be done in terms of password cracking? First of all, hardware acceleration. So there were already several talks covering GPUs. How could we use different type of GPUs? What cards could be faster, etc. Another approach is FPGAs. So you could write basically microcode for those FPGAs, and then you could purchase them in amounts, but they are fast but really very expensive compared to GPUs. We could use distributed network attacks, and this was covered yesterday as well, to use multiple computers to work on to decrypt passwords. Rainbow tables. We could tweak password generation rules, and I mean this could be really very efficient. There were numerous talks yesterday covering generating word lists from Wikipedia, even IRC, etc. Markov chains, trying to generate and check passwords that might sound, well, say English or Norwegian, etc. Usually, I mean, when you enforce a user to comply with some kind of a really weird password policy, as Per told us today, users just change their password just a little bit. Okay, my password was Oslo 12, now it's Oslo 13, etc. And I mean, we see a lot of such cases. Another approach might be RAM analysis. And what's RAM analysis exactly? So when an application is executed, sometimes passwords are stored in memory. Let's take for example Mac OS X. We've notified Apple several times, and it's been over a year now. But still, when you're logging into Mac OS X, they would store your login password unencrypted in memory. It's always there. Windows is slightly better in that respect. Passwords are stored in memory as well, but they are encrypted. So basically you can just get a RAM dump, try to find all the words there, and find a password. You could also use RAM memory images to generate very good word lists, because chat history, emails, and some other information is retained in RAM. Encryption keys. If you have full disk encryption software, be it BitLock or TrueCrypt or FileVault or PGP, the vendor doesn't really matter. If a drive is mounted, encryption keys are present in memory in order to access the data. Applications. If you have an Office document open that's password protected, obviously Office would retain encryption key in memory. The same goes for archives, PDFs, etc. Well, archives are usually not open for that long, but I mean, as long as you work with a document, encryption keys for this document are retained in memory. So what could be done about that? First of all, we need to acquire memory image. There are multiple approaches there. First of all, trying to capture live memory images. So FireWire direct memory access. It's rather efficient. It works very well for Windows PCs. You can just use a boot drive, boot a second PC, and connect with a FireWire cable and get a RAM dump. One of the drawbacks, it would capture only the first 4 gigabytes of memory, because this is the way that direct memory access works. And when we found the same problem with macOS, we notified Apple, and now there is a patch there that has password name in it. And actually, if you lock down macOS PC that uses file vault, direct memory access is disabled for FireWire. But if you have like a guest logging, anything, then a FireWire is enabled, and you could use the very same approach to capture live memory image using FireWire. You could also use FireWire memory adapter to do the very same thing with Thunderbolt. Another way to create live memory images, it's not live after you turn off the computer, but you could actually cool down memory chips. It's quite a show. But I don't actually see any, let's say, police officer walking to the scene with a can of compressed air trying to cool down memory chips and trying to get any information from there. But what we found during some tests is that modern PCs, modern laptop memory chips, they do retain memory contents for, let's say, several seconds. So basically, you could remove a battery, you could reset the computer, you could load a very tiny version of Linux, and you can dump your memory on a USB thumb drive. And this way, you could save like 90% of memory contents. It works easily. It won't require you to use compressed air or anything. It's really very efficient. And what we work with a lot of law enforcement in the US, with a lot of police departments. What we teach them is you just never turn off a PC, because the state is priceless. If you turn a PC, you could use encryption keys, you could lose mounted drives, and if a password is secure enough, you could just never get into TrueCrypt or BitLocker. And let's say TrueCrypt allows you to set up hidden volumes, and it's practically impossible to detect those kind of volumes if the state is lost. When we talk about memory images, hibernation file is basically a memory image. And what's interesting about hibernation file, except that it contains all the brand functions, is in Windows there's volume shadow copying mechanism in TFS. This allows you to store multiple copies of the same file if you have enough space on your hard drive. What this means is for some users, you could have, let's say, 5 copies of hibernation file, and that all this could be several weeks ago. This allows us to find, let's say, encryption keys if the drive was mounted 2 weeks ago. This could be a time saver. All right, let's do, live memory imaging works really fast. So this allows us to do a very short demo of the software. All right, it works. So for this one, we'll take Windows hibernation file. So the software would scan the whole hibernation file. It would try to locate all memory segments that might have information that's similar to Windows logins, and then gets those logins decrypted, because I'll repeat myself, Windows will not store encrypted passwords in memory. So it takes a little bit of time, not that long, especially compared to brute force attacks. But this process does not depend on how complex a password might be. If you could type in a passphrase, you could use the most extreme password policy, but if you can get Windows hibernation file, then you have a password. of all the users that were logged in. All right, so we got our password. It's approximately 30 characters in length. Good luck trying to brute force it. And it took us 53 seconds. And once again, there could be multiple copies of the hibernation files sitting there. So my advice is you just should disable hibernation or use BitLocker to secure the hard drive. All right. Pagination file. Well, pagination file is not like memory image itself, but it has pages, and some of the pages might contain encryption keys as well. So this could also be a very useful source of information. Then memory dumps. So how to create a memory dump? There are several command line tools. Some of those are free, like dump it from Moon Solstice. It's really very good. Memory imaging tools are included in most of the computer forensics tools available. There are some tools that run over the network, but what's important is that you still need to have enough privileges in order to run those tools. So this is slightly different from using FireWire, reboot attack, etc. So let's do another very short demo. So we'll scan just one folder of hard drive for encrypted files. And this is usually really fast. So we found a bunch of files. Let's just select those files, click recover, and tell the software, okay, remove all the tags. I could drag and drop brute force dictionary tags, I could combine them. But this time we'll need to extract encryption keys. And this time I'll select memory image. I could actually select multiple memory images. I could throw in a pagination file. Basically, I could throw in any kind of binary file. If the software finds encryption keys there, it would try to see if those encryption keys would fit to any of those files in the list. Just to speed up the process, let's leave just a memory image. Click recover. So the software is now looking for regions in memory that might possibly contain AES encryption keys. And it also creates a list of all those possible encryption keys. And in a little bit, the software would start testing each of the keys in the list against those files. So sometimes we could find thousands of those keys, but testing a single key is a very cheap operation in terms of time. I mean, it's like going through this list, it's like testing 1,000 passwords. This doesn't really take much of a time. As you can see, the software found 12 possible encryption keys in memory. And we have a match here. So we don't know the actual password, but as we know the encryption key, as the encryption key works for the file, we could create an encrypted, unprotected copy of this file. So this is a password. This is 4 characters, 1 capital password. So once again, go try and find this kind of a password using a dictionary. I mean, this could possibly be found using a dictionary, but this also works with all kinds of complex passwords. And the whole process took us, let me see, less than 2 minutes. So, live memory analysis, it's very fast. It's guaranteed. It does not depend on how complex a password might be. It would always provide you with the result of encryption keys or passwords are in memory. Problems with this kind of approach. You actually need to have a memory image. This could also be a hibernation file. This could be multiple versions of hibernation file. You could try H-file to find encryption keys there. There could be some success. And this obviously won't work for data that's at rest. Basically, if you turn down a PC, if there is no hibernation file, you cannot apply this. How to mitigate the risks? Disable hibernation. Enable full disk encryption. And never leave your computer unattended. That's it. So I was trying to go really fast. Any questions?
I thought we were going to see a Thunderbolt demo.
Oh no, it's probably next year.
Okay.
Still working on that one?
Yeah.
Yeah.
I have two questions. One, I noticed you didn't mention volatility. Is there a particular reason for that? Have you tried it and not got on with that as a memory analysis tool?
So there are some features that our software has that volatility doesn't. We are actually developer of our own software, so that we know exactly how it works.
And the other question was, you said you were only looking for AES keys. That presumably you're searching for the key schedule, rather than sort of areas of high entropy.
No, we are not using entropy. It would provide too many results.
Can you talk a little bit about what techniques you're using to find the keys in memory?
I'm afraid I won't disclose this in great detail. But I think there's a fair amount of research papers that are now available about searching for encryption keys in memory. Yeah.
Also support for other operating systems, for example, Lux encryption keys?
No, we are not supporting Linux encryption at the moment, but we do support Apple Firewall too. So basically, we have not received enough requests for Linux support at the moment, but I don't see any issues with that. The only approach might be is like to store encryption keys for full disk encryption software in registers, in special registers of CPU. This way they are never present in memory. So.
I have a question. Many years ago, the so-called TPM was introduced, the Trusted Platform Module, and nobody found any use for it until Windows introduced it to BitLocker. You can now use BitLocker with the TPM, which means that your disk can only be decrypted if it's installed in that very same computer. So you cannot take the disk out, put it in a different computer and decrypt it.
Yes.
I think this is a crap solution. What do you think we do?
This is a false statement. I mean, if you can boot this computer with a TPM chip, if you could probably use FireWire to create memory image, and encryption keys for this drive would be in this memory image. you could safely pull out this hard drive and to use encryption keys on a different machine.
So that means for forensics, they can no longer work on an image of the disk. They have to work on the very machine.
No, that's not true. Once again, so encryption keys are in memory image, and you can use those encryption keys. You won't longer need a TPM chip.
It's a joke.
Yes.
So that, but if the encryption is being done by the drive, does it
yes.
out of RAM?
Yes, obviously, I mean, there are two types of hard drive protection there. First, there is like user is prompted for a password. And obviously this is a joke because you just go to a service area of a hard disk drive and tell, okay, the drive is no longer password protected, and that's it. It just takes a couple of minutes. But there are some drives from several vendors, like Seagate, etc., that do a real hardware encryption. And this is really very secure at the moment. Yes.
Are those all on our SAS like enterprise line, or some of the other ones actually?
Excuse me?
The Seagate drives that actually do proper encryption, those are those all on the SAS enterprise line?
No, they're not.
Okay.
But sometimes, I mean, officially, let's say you cannot import those drives in Russia. And I'm not sure about export shows. I'm not sure you can export those kind of drives safely from the US.
Well, yeah, not without an export license, because
Yes.
their AES it's greater than 56 bits. So yeah.
Thank you.